Okay, so let's talk about hypothesis testing. Uh, Hypothesis is something we believe about the population. Okay, something we believe about the population, something we think that might happen in the population. Okay, that is our research hypothesis. Usually, we develop the research hypothesis based on economic theories and previous researches. Okay, and also sometimes we base our hypothesis. We develop our hypothesis based on the sample statistic. Okay, based on what we see in the in the sample that we get to estimate the model. So here, in the context of econometrics, our hypothesis is about our model regression coefficient. Okay, our hypothesis is what we believe about the regression coefficient. All right, and um, in this course, we will do some tests about the regression coefficients. The first one, we want to test an individual regression coefficient. So when we test an individual's regression coefficient, we are testing the individual effect of one independent variables on the dependent variables. Okay, so you see that in our model, there may be many independent variables, but when we are testing an individual's regression coefficients, we are just test the only the individual effect of the independent variables uh, associated with that regression coefficient only. Okay, and for if you want to test an individual regression coefficient, we have some approaches to use. You may use the confidence interval approach to test an individual regression coefficients. You can also use the test of significant approach. And finally, we will find out more about the p-value approach, which is mostly used in scientific researches. Okay, and the second test is the test of a group of regression coefficient. Okay, which means that we test the joint effect. Okay, not the individual effect of an independent variables on the dependent variables only, but we are testing the joint effect of a number of independent variables on the dependent variables. Okay, it is also called the multiple linear restriction test. Okay, and for this one, we will investigate two types of tests, which is the overall significance of a sample regression model, and the second one is the joint significance of a group of variables. Um, and finally, the third test that we study in this chapter is the test a linear combination of a regression. Test a linear combinations of the regression coefficients. Okay, although this test involve more than one regression coefficient, it is not the multiple linear restriction test. It is one restriction test, but we are testing a linear combinations of the regression coefficient. Okay, and the most familiar test for this type is the equality of two regression coefficients, which means that we test whether the individual effect of these independent variables on the dependent variable is the same as the individual effects of another independent variables on the dependent variables. Okay, so that is three types of tests. we will study in this chapter. Let's move on to H type. And before we talk about the test of the individuals regression coefficients, let's talk about hypothesis testing first. So hypothesis is the assumptions about the population parameters in the context of econometrics. So it is what we believe about the population parameters. For example, we we believe that the regression coefficient beta 2 might be greater than 0. Okay, or we believe that, okay, when the disposal income increased by $1 million, the average expenditures will increase by less than 5,000 or 5,000 dong. Okay, all right. We can believe that the mean weight of an FTU student is 55 kilogram, for example. So those are the assumptions about a population parameters. Remember that. It may be the assumption about a population parameters can also be expressed in the relationship between the variables in the population. Okay, and remember that we test hypothesis. We do the hypothesis testing about the unknown population parameters, not about the known sample statistic. Okay, so we can easily calculate the sample statistic and get the exact value of it. That's why we are not testing the sample statistic. We will have to test the unknown parameters in the population regression model, which are the betas, okay? Not the beta hat, remember that. So there are always two opposing hypotheses. We have HO, the non-hypothesis, and the alternative hypothesis H1, or sometimes you can see some book write the alternative hypothesis as HA. Okay. Now H1, HO and H1. The non-hypothesis HO, it reflects that there will be no observed effect for your experiments, which means that what you see in your experiment or what you see in your sample, okay, what you get from your sample data is not what we see in the population. Okay, so the non-hypothesis will reject what we see in the sample. Okay, and it is assumed to be true until the evidence indicates otherwise, which means that when we develop an HO, okay, we develop the non-hypothesis, it is assumed to be true at first. Okay, and however, HO is what we want to reject because it does not reflect the what you see in the sample. Usually when we analyze the sample, okay, when we use the sample to estimate the model, we usually expect that our sample represents our population. Okay, and that's why we will use the sample statistic to test for the population. But for the non-hypothesis, it rejects what we find in the sample. Okay, that's why it is what we want to reject. And HO at first is assumed to be true, but we usually want to find the evidence to reject the hypothesis HO. Okay, and the alternative hypothesis H1, the alternative hypothesis is an alternative to the non-hypothesis. It is a different statement. Okay, it is a different statement from the non-hypothesis. And remember that both the non-hypothesis HO and the alternative hypothesis H1 are all about the unknown population parameters. Okay, and in contrast to the non-hypothesis, the alternative hypothesis usually reflects that there will be an observed effect for our experiments, for our sample analysis. Okay, analysis. Okay, so it usually support. Okay, the H1 hypothesis usually support what we see in the sample. Okay, and usually H1 is what we want to prove to be true. Okay, H1 usually is what we want to prove to be true. So what we ask in the exercise, or what is your belief, okay, that will be reflected in the alternative hypothesis H1. Okay, H1 will be what you believe, what you want to prove to be true. Okay, all right. So in doing hypothesis testing, okay, our purpose is to reject the non-hypothesis, and we have more evidence to support the alternative hypothesis. Okay, that is our purpose when we do the hypothesis testing. So that's why H1 usually have H1 usually contains what we believe and what the exercise usually asks you to prove. Okay. All right. Now let's talk about the hypothesis testing for an individual regression coefficient beta z, with z, okay, is from 1 to k. Okay, it can be, okay, it can be 0 to k. You can also test the intercept. Okay, but usually we want to test the regression coefficient, the slope, because they show the effect, the individual effect of the independent variables on the dependent variables. Okay, now if we want to test an individual regression coefficient, we are testing the individual effect of an dependent variables, independent variables on the dependent variables, whether there is an individual's regression, individual effect of these independent variables on the dependent variables. So what is individual effect? So you can see that. Now, what is individual regression coefficient? So this may be our dependent variable y, for example. This is our dependent variables y, and these are the information contained in y. Okay, contained in y. So we use x1 and x2, for example, to explain for the value of y, to explain for the informations in y. Okay, so for example, this may be our x1 here. Okay, this may be our x1, and x1 explain this part of the information in y. Okay, so these are the information in y that is explained by x1, for example. All right, and we also have x2 to explain for the information in y. Okay, so maybe in the case when there is no correlation between x1 and x2, which means that x1 and x2 are independent, there's no correlation between them. Okay, so this one will be x2, and this part is the information that x2 explain for y. Okay, these two parts of the information in y are different parts. So which means that there's no intersection between these two areas. So these two areas are independent of each other, and they are called the individual. Okay, this one is the individual effect of x1 on y, and this one is the individual effect of x2 on y. Okay, this is the case when there's no correlation between x1 and x2. Okay, but sometimes there might be a correlation between x1 and x2. So we will have our model like this. So this is the information of y. So x1 explain part of the information in y. So this is our x1. And x2, which may have a correlation with x2, and is also explain a part of the information in y. And because it has a correlation with x2, there may be an intersection like this. Okay, so this one is the part of the information in y explained by x1, and this one is the part of the information in y explained by x2. Okay, all right, but you can see that there is an overlap information here. Okay, so this one is not the individual effect of x1 and x2 in the dependent variable y. This one is not the individual effect. Okay, here we have this part, this area. Okay, the pink area is the individual. This one is the individual effect of x1 on y. And this yellow area, okay, this one is the individual effect of x2 on y. Okay, so now we are testing the individual effect of each independent variables on the dependent variables. Okay, we are not talking about this overlap information here. Okay, we just talk about the individual effect of the one independent variables on the dependent variables. Okay, now let's do that to see whether there is an individual effect of one independent variables on the dependent variables. Sometimes you can see that sometimes for some case, if there is a very high correlation between x1 and x2, for example, in this case, so this is our y, this is our x1, okay, and because there is a high correlation between x1 and x2, for example, in this case, we have a high correlation between x1 and x2, okay, this is our x2. Okay, so the individual effect of x1 and the individual effects of x2, okay, they are too small, too little individual effect of the independent variables on the dependent variables. Because they are too small, they are too little, that it becomes insignificant. Okay, so in that case, we will say that because the individual effect of the independent variables on the dependent variable is not significant, we say that there is no individual effect of x1 on y, or we can say that there's no individual effect of x2 on y. Okay, for the case when the individual effect is too small, is insignificant. Okay, All right, so now let's do a test to see whether there is an individual effect of an independent variables on the dependent variables. Okay, any questions here? All right, let's move to the individual effect, the testing an individual regression coefficient. Okay, we have some tests. We will have the hypothesis is about one individual regression coefficient, beta z. We have two-sided testing and one-sided testing like this. Wait a minute. Okay, we have here the two-sided testing, or we can call it two-tail testing. Okay, we may have one-sided testing. Here we have beta z. HO is the non-hypothesis and H1 is the alternative hypothesis, is what we believe to be true. Okay, so beta z is our unknown population parameters. Beta z here is the unknown population parameters, and beta z star, okay, beta z star is the suspicious, okay, is the suspect value of the unknown population parameters. Okay, maybe it is usually a certain number, maybe 0, maybe 1, maybe 2, maybe 3, and so on, depends on your hypothesis. So beta z star here is the suspect value of the unknown population parameters. All right, so we have to make the difference between, we have to tell the difference between two-sided testing and one-sided testing, because the critical value that we use to construct the confidence interval or way to do the test of significance will be different for two-sided test and one-sided test. So how can we know that it is a two-sided test or one-sided test? How can we know whether the test we are doing is a one-sided test or a two-sided test?
If H1 is a different side, is BJ different from BJ star, it means that is two side. But if it is smaller or bigger, then it is just one side. We focus on the H1.
Yeah, right. That's right. Just look at the alternative hypothesis H1. You can see that you can realize whether it is a one-sided test or two-sided test. Okay. If we see a different side here in the alternative hypothesis, which it means that it will be a two-sided test. But if we see the larger side or lesser side, okay, the smaller side like this, okay, it will be a one-sided test. Okay, so it will determine one-sided or two-sided test will determine the critical value that we use in the test. All right, now as we say, we have different approaches to test for an individual regression coefficient. All right, so let's see here. The first one is the confidence interval approach. The confidence interval approach, in this one, you have to do 3 steps in order to test an individual regression coefficient by the confidence interval approach. The first one, you have to state the hypothesis. This is the first step for every approach. Okay, in every test, in every approach, the first step is to state the hypothesis. The hypothesis will determine the test statistic you use, will determine the critical value that we need to use, and will determine the decisions Okay, or we can say that the decision rule um, or the reason of acceptance or rejection or something like this, and so on. So that's why the first step is to state your hypothesis, what you are testing. Okay, now for this one, there may be a two-sided test. Okay, we may want to test a two-sided test, and then after you have stated the hypothesis, you will have to construct the confidence interval for our regression coefficient. Okay, and then after you have construct the confidence interval for the regression coefficient, you will make decision whether to reject the null hypothesis HO. Okay, so the decision here is very easy. The decision rule is very easy. If beta 1, if beta star, which is the suspect value, fall into the confidence interval that you have construct in the second step, then you cannot reject HO. Okay, but if the suspect value beta z star does not fall into the confidence interval, then you can reject the null hypothesis HO. Now let's see the reason behind this. Okay, so for example, you may want to you may want to do a two-sided test. For example, we have H. Let's wait some minutes. 1 minute. Okay. Now, for example, we want to do a two-sided test. We have HO. Okay, is that the unknown parameters beta z, okay, is equal to the suspect value, which is beta z star. Okay, and the alternative hypothesis H1 is that the unknown parameter beta z is different from beta z star. Okay, so this is a two-sided test. Now, in the second step, you have to construct the 1 minus alpha times 100% confidence interval for beta z. Okay, so what is it? The 1 minus alpha times 100% confidence interval for beta z. Do you still remember it? What is the formula for it? What is it? What is the formula for the confidence interval for beta z? The two-sided confidence interval.
Beta j star minus t alpha over 2 times
Beta
s
z hat. Beta z hat. Yeah.
minus
t
alpha over 2.
Yeah.
With df is n minus k minus 1 times
Yeah.
se times se of bj hat.
Yeah.
That's one. That's first one. The second one will be the bj hat plus t alpha over 2 times se of bj's hat.
Okay, beta z hat. All right. So this is the confidence interval for beta j. So, all right. So it means that, okay, beta z fall into this interval. Okay. So if beta z star fall into this interval, it means that there will be a chance that beta z is equal to beta z star. Okay, so because this one is the confidence interval for beta z, then we have beta z hat, okay, minus t alpha divided by 2 times se of beta z hat. Okay, less or equal to beta z this one is less and equal to beta z hat, okay, plus T alpha divided by 2 times SE of beta z hat, okay? And if we also have beta z star fall into this range, then we also have beta z hat minus T alpha divided by 2 times SE of beta z hat is less or equal than beta z star, okay? Or is less and equal than beta z hat plus D alpha divided by 2 SE of beta z hat. So there will be a chance, okay, there will be a chance that the actual value of the unknown parameters is equal to the suspect value, okay? And because of that, okay, because of that, we cannot reject the null hypothesis HO, okay, if the suspect value beta z star fall into the confidence interval for beta z, okay? But if beta z hat star does not fall into the confidence interval for beta z, okay, so we can say that, okay, beta z star is different from beta z. Beta z fall into this range, but beta z star is not in this range, okay? That's why we can reject the null hypothesis, and we say that, okay, so beta z is different from beta z star, okay, at the level of significance of alpha, or at the confidence level, the level of confidence of alpha minus 1 minus alpha, okay? Okay, that is the decisions, why we have that decision rule, okay? If the suspect value fall into the confidence interval, you cannot reject the null hypothesis. But if the suspect value does not fall into the confidence interval, then you can reject the null hypothesis, okay? Now, come back to our example here. Come back to our example about here. We have in the previous class, you have construct the confidence interval for the coefficients on Tn. Okay, now let's do a test and using the confidence interval approach to see whether the coefficient, the regression coefficient on Tn's is statistically different from 0. Okay, so I may ask a questions like this. Okay, I may ask a questions like this. So I'm going to change the color. At 5% level of significance, okay, at 5% level of significance, okay, is the regression coefficient on Tn statistically statistically different from 0. Okay, can I for the same problems, I can also ask that, okay, so at 5% level of significance, is the regression coefficient on Tn, okay, statistically significant? Okay, I can also ask that, okay, at 5% level of significance, does the independent variables Tn, oops, okay, significantly actually affect the dependent variable Ct. Okay, so this is three ways of asking the same questions. Okay, that you have that mean that they mean that you have to test for the individual regression coefficient on Tn. Okay, it's just different way of asking the questions. Okay, is the regression coefficient on Tn statistically different from 0, or is the regression coefficient on Tn statistically significant? When the regression coefficient is different from 0, it means that, okay, so the independent variables Tn's, okay, significantly or actually affect the dependent variables. Okay, so there is just some way of asking the same questions, so remember that. So here, for these questions and this exercise, you have construct the 95 confident interval, 95% confident interval for CT, for the regression coefficient on Tn. So just do the test, okay? Do the test using the confident interval approach. What will you see? Can you research the null hypothesis or not? Okay, so here, what is your hypothesis? The first step, we have three steps. Okay, so the first one is to state the hypothesis. So what is our hypothesis here? What is the hypothesis here? Class, step one, state the hypothesis.
Beta j is equal to 0.
Okay, we have HO beta Tn, for example, or you can call it beta 1. What is it? HO
is equal to 0.
Yeah, this one is equal to 0. And H1 beta Tn
is different from 0.
is different from 0. So our suspect value here is 0. Okay, 0. Now, step 2, you have to construct the 95% confident interval for beta Tn. Okay, so what is the 95 confident interval for beta Tn?
It's from 0.76 to 0.83.
Okay, so this one is the 95% confident interval for beta Tn's. So step 3, just make the decision. Okay, make the decisions. So is the suspect value, okay, is the suspect value belong to the confidence interval? Fall into the confidence interval for beta Tn?
No.
It is not.
Okay, so we have that the suspect value zero is not belong to this confidence interval. Okay, then we will reject or do not reject HO.
We reject HO.
Reject
We
HO.
will reject HO. Okay, we reject HO, and as we reject HO, we have more evidence to support the alternative hypothesis. Okay, and then we say that at 5% level of significance, okay, the regression coefficient on Tn is statistically significant or is statistically different from zero. Okay, so that is our conclusions. Okay, we reject HO and we conclude that at 5% level of significance, the regression coefficient on Tn is statistically significant, or we can say that it is statistically different from zero. Okay, we can also say that the independent variable Tn significantly affect the dependent variables. Okay, so that is the confidence interval approach. For one-sided test, we can easily use the confidence interval approach, but in fact, in practice, we usually use the second approach to do the test for one-sided test on regression coefficient. That is the test of significant approach. In the test of significant approach, for one independent variables, for one individual regression coefficient, we will use a t-test. Okay, now let's see how we can use the test of significant approach to test for an individual regression coefficient. All right, now for the case of test of significance. So for an individual regression coefficient, you have to use a t-test to test for the significance of that. Okay, so let's remind. Okay, right. Let's remind the step that we need to do in doing a t-test. So the step one, okay, the same as every test, we have to state the hypothesis. In step two, we have to calculate the test statistic or the observed value of t. Okay, we call it TS. All right, so TS here is equal what? This one is the observed value. Okay, the observed value of the unknown parameters minus the suspect value of the unknown parameters and divided by the standard error of the estimate. Okay, so this one is the test statistic. So why do we calculate the test statistic like this? Okay, we will talk about it in the next slide. Okay, and step three. In step three, you have to determine the critical region of the rejection zone. Okay, in order to determine the critical region of the rejection zone, you have to find the critical value of t. Okay, the critical value of t, you can look for the value of it in the in the statistic table, okay, statistical table for t distribution. You can also use Excel to find the critical value of t, okay. And when you find the critical value of t, remember to identify the degree of freedoms of the distribution and the level of significance for the test. Okay, so finally, step 4, you will draw the conclusions based on the observed value of t and the critical reason. Okay, now this one, step 2, you have to find the test statistic, you have to calculate statistic. All right, so do you remember the formula for TS that we talked about at the beginning of this chapter? What is the formula for the observed value of t? What is it? Do you remember the formula for the observed value of t that we talked about at the beginning of this chapter? How do we calculate t? How do we calculate the observed value of t? Do you remember the formula for it? Okay. All right. Though the formula for it is like this. Okay, we have a t as the observed value of t equal the observed value of beta z, which is beta z hat. Okay, minus, what is it? The actual value. Yeah. No.
Beta j over SE of beta j
yeah.
hat.
SE of beta z hat. Okay, this is the formula to calculate the observed value of t. Okay, but corresponding to the observed value of beta z hat. But here you see the difference. We take beta z hat minus beta z star divided by the standard error of beta z hat. So what is the difference here?
Beta j and beta j hat, beta j star.
Yeah, right. Beta z and beta z star. That is the difference. Here we have beta z star in the formula. Why do we have that difference? Okay, so this one, the observed value of t here is calculated when we assume that the null hypothesis is true. So remember, recall our null hypothesis HO is that beta z, is that beta z equal beta z star. So that when this one is true, okay, when this one is true, we have the observed value of t is equal beta z hat minus beta z star and divided by the standard error of beta z hat. Sorry. Okay. So this one is calculated when we assume that HO is correct. Okay. All right. So if HO is correct, which means that beta z is equal to beta z star. All right. Then if beta z is equal to beta z star, then you can construct the 1 minus alpha times 100% confidence interval for the observed value of beta z hat. Okay, so let's look at this. So this is the distribution of beta z hat. Okay, this is the distribution of beta z hat. You have the expected value of beta z hat is beta z. And when we assume that the HO is true, HO is correct, then we have the expected value of beta z hat is beta z star, like this. Okay, so from this one, you can construct the 1 minus alpha times 100% confidence interval for the observed value of beta z hat. Okay, we will have the confident 1 minus alpha times 100% confident interval for the observed value of beta z hat. Okay, that will be beta z star, yeah, minus t alpha divided by 2 times standard error of beta z hat. Okay, and to beta z star minus plus alpha divided by 2 times SE of beta z hat. Okay, we construct an interval around the mean. Okay, T alpha divided by 2 standard error in either side of the mean. Okay, this one will form a 95%, sorry, it's not 95, but 1 minus alpha times 100% confident interval for the observed value of beta z. So, for example, alpha equal to 5%, okay, alpha equal 5%, then, okay, when you take a random sample, from the population and calculate the observed value of beta z hat, so the value of beta z hat has a very high chance, okay, say 95% of falling into this interval. Okay, so when you take a random sample from the population, okay, and calculate the observed value of beta z hat, there will be a very high chance, okay, maybe 95% chance that the observed value of beta z hat will fall into this confident interval if HO is true. Okay, so this range is called the reasons of acceptance. Okay, this one is called the reason of acceptance of the null hypothesis. Okay, it is called the reason of acceptance for the null hypothesis. Okay, and which means that if beta z hat fall into this interval, then we can accept the null hypothesis, or we can say that we cannot reject the null hypothesis if beta z hat fall into this reason of acceptance. Okay, all right, and because the distribution of t and beta z hat is quite equivalent. Okay, so we will have the distribution of t like this. This is t. Okay, our observed value of t in corresponding to each observed value of beta z hat. Okay, so here, if beta z hat equal beta z star, then the observed value of t will be 0, which is the mean of the t, observed value of t. Okay, so here, if beta z hat equal beta z star minus t alpha divided by 2 and times SE of beta z hat, okay, just replace it into this formula and you can calculate the t observed here. So the observed value of t in corresponding to this point, to this value of beta z hat, will be minus alpha divided by 2. Okay, will be minus alpha divided by 2. And this one, if beta z hat is equal to this one, which means this point, okay, then just replace beta z hat into this formula. You will get the observed value of t here is t alpha divided by 2. Okay, is t alpha divided by 2. So this one, okay, this area is called the reason of acceptance for the reason of acceptance for the null hypothesis. Okay, and these two area outside the region of acceptance is called the reason of the critical reason, or the rejection zone, for the null hypothesis, which means that if the observed value of t fall into this range, then we can reject the null hypothesis. Okay, so we have here the reason of acceptance, and also we have the reason of rejection. The reason outside the confidence interval, okay, this one outside the gray area. The gray area is the reason outside the reason of acceptance is called the reason of rejection, and we call it the critical reason. Okay, and here we have the reason of acceptance for t. Okay, this one is for beta z hat. This one is for the corresponding observed value of t. So here, if this area is the reason of acceptance for the null hypothesis, so equivalently in the distribution of t, we will have this one minus alpha t minus t alpha divided by 2 to alpha to t alpha divided by 2. This one is the reason of acceptance for the null hypothesis. But if the observed value of beta z hat fall into this gray area or this one, okay, and accordingly, the value of t, the observed value of t fall into this area, okay, then we can reject the null hypothesis, and we call this gray area are the reasons of rejection or the critical reason or rejection zone, okay, for the null hypothesis. And a statistic is said to be statistically significant if the value of the test statistic lies in the critical reason. Okay, so a statistic like beta z hat, okay, a statistic like beta z hat is said to be statistically significant if the value of the test statistic, which is t, lies in the critical region. Okay, so if t fall into the critical region, the gray area here, okay, so beta z hat is said to be statistically significant. All right, okay. Any questions here? This is the definition of reason of acceptance for a test and the reason of rejection for a test for the null hypothesis. Any questions here? Okay, good. And the same for the one-sided test. Okay, you can determine the rejection of acceptance and the region of rejection for one-sided test. So this is the decision rule for a t-test, the test of significance. Okay, so if the observed value of t fall into the rejection zone or the reason of rejection, then you can reject the null hypothesis. For a two-tailed test or two-sided test, we have here, this one is the alternative hypothesis, where beta z is different from beta z star. Then the rejection zone, okay, usually we call it the W, the rejection zone, we call it the W, okay. It will be from minus infinity, to minus infinity to minus t alpha divided by 2. And, okay, what is it? T alpha divided by 2 to plus, okay, positive infinitive. Okay, and for the right tail, now is a little bit complicated for the right tail and for the left tail. Okay, so for the right tail, look at this. Now we have a larger psi in the alternative hypothesis. Then the side of the rejection zone will also be larger side like this. For the left tail, we have smaller side in the alternative hypothesis. Then in the rejection zone, we will also have a smaller side. Okay, but remember that if we have a larger side, then the critical value must be a positive one. Okay, and if we have smaller side, the critical value must be a negative one. Now, why do we have positive and negative here? Okay, so look at this. Look at the reason of acceptance and the reason of rejection. You can see this for what is it? This for the two-sided test, for example. We have this one is the observed value of t. We have this one is the expected value of t. Okay, we have this one is minus t alpha divided by 2, and this one is t alpha divided by 2. Okay, so you can see that this one is the reason of acceptance, and the area of a reason of acceptance is very large. Is 1 minus alpha. Okay, it might be 95%, it might be 99%, it might be 90%. Okay, so the area of the reason of acceptance is a large one. Okay, but the area for the critical reason or the reason of rejection is a small one. Okay, this one is small. The value of it, okay, the sum of these two areas is just alpha. It might be 0 0.0.5, 0.0.1, or 0.1. Okay, this area is a small one. Okay, a small area. And the same happened for one-sided test. For one-sided test, okay, for example, HO is beta Z equal beta Z star, and H1 is beta Z larger than beta Z star, for example. Okay, then we will have the reason of acceptance like this. Okay, so here is T. This one, we have expected value of 0. For this one, you have to construct a confidence interval. Okay, so the reason of acceptance here will be from minus infinity to T alpha. Okay, so this one is the reason of acceptance 1 minus alpha with the area of 1 minus alpha. And this one, the area of alpha is the reason of rejection. So the reason of rejection always has a small value. Okay, it is a small area in the distribution of T. So that's why if we have the rejection zone, okay, if we have the rejection zone is T of the value of T larger than a value, then that value must be a positive number. It must be a positive number, okay, so that the rejection zone or the reason of rejection here will be a small area. If it is a negative number, okay, then the rejection zone will become a big reason like this. Okay, so it is not the case for a rejection zone. Okay, so if for the rejection zone we have a larger side here, then this one must be a positive number. Okay, that is T alpha. Okay, but for one-sided test where we have beta z h1 is beta z less than beta z star, okay, then the rejection zone must be, okay, a small area, which means that, all right, we have here t minus t alpha. This one is alpha minus 1 minus alpha, and this one is alpha. Okay, and this is the rejection zone. If the reason of rejection is that t, the observed value of t, ts, is less than a value, then that value must be a negative number. This one must be a negative number, so that the reason of rejection here has a small value. Okay, the area has a small value. Okay, if this one is a positive number, then the reason of rejection here will be a very big area. Okay, will be a very big area, and that is not correct for the rejection zone. Rejection zone, or the reason of rejection, are the area that has a very small number. Okay, small value. Okay, all right, so remember that this is the decision rule for a test of significance, for a t-test. Okay, so now let's use the test of significant approach to test for, okay, so we have do the test for the coefficient on Tn. Now let's do a test for the coefficient on Ts. Okay, so here, let's answer the questions. My questions here is, my question here is, at, sorry, now, my questions is, at 1% level of significance, no, okay, does TS have a positive effect on the dependent variable CT. Okay, so at 1% level of significance, does TS have a positive effect on CT? Okay, let's do this using the test of significant approach. We have 4 steps. Just follow 4 steps that we have listed before. Okay, any volunteer? Wait a minute. Okay. Okay, so we have Huyền Trang and Quỳnh Phương volunteer for this one. I think that Huyền Trang already has an extra point. Quỳnh Phương, do you have any extra point yet?
No.
Okay, so okay, happy to do this one. This one. Okay. Now we have 4 steps. What is the first one?
The first one is establish hypothesis.
Yeah, okay, we want to state the hypothesis, non-hypothesis, and the alternative hypothesis. So what is our non-hypothesis?
Our non-hypothesis is beta 2 smaller or equal to 0.
Okay, smaller or equal 0, and beta 2 for
Beta
each
2
one.
greater than
Mhm.
0.
Okay, so when we say that TS has a positive effect on CT, it means that the regression coefficient on TS is greater than 0. Okay, so we have here H1 is that beta 2, the regression on TS is greater than 0. All right, so step 3, what is it?
Step 2, we find the test statistic.
Yeah, we have to calculate. We will have to calculate the test statistic. Okay, what is it? TS equal.
TS equal 3.75.
Okay, the formula first. We have beta 2 hat minus
0.
0 and divided by the
Standard
error of beta 2 hat. Yeah, and just plug in the number.
It is 0.015 divided 0.004.
004 like this. Okay.
Yes.
What is the value of TS?
Is equal 3.75.
Yeah, 3.75 exactly. And step 3, what is it?
We determine the critical region.
Yeah, the critical reason. Critical reason. In order to determine the critical reason, we have to determine the critical value of T. What is the critical value of T?
It is T 0.1 and 27.
Yeah, 27. What is it? Just look for the value in Excel.
Equal 2.47.
47. Okay, we got 47. So what is our critical reason?
Critical reasons is 2.47 and infinity.
Yeah,
To
from
yes.
2.47 to positive infinity, like this. Okay, so step 4. Okay, so is the observed value fall into the critical reason? That
Um, we have 3.75.
uh, we have the observed value of TS, okay, fall into the critical reason. Okay, so
Yeah. So we reject non-hypothesis.
we research HO, the null hypothesis, and then what is our conclusion?
Our conclusion is at 1% significant level. Mm, the regression coefficient on TS is
Mhm.
statistically greater than 0.
Okay, so at 5% level of significance, the regression coefficient on TS is statistically larger or greater than 0. Okay, thank you. Or you can say that as because the questions is that does the TS has a positive impact on CT, then you can say that at 1% level of significance, then we have TS has a positive impact or effect on CT. Okay, is also okay, or you can say that the coefficient, the regression coefficient on TS is statistically greater than 0. Okay, thank you. Thank you, Quỳnh Phương. All right. Any questions here? Just follow the step we're talking about. All right. Okay, now just let's take 20 minutes break, and then we will come back at 8:30. Okay.
Teacher, can I ask you a question?
Yes, I'm here.
Okay. So, um, when constructing a model, is it
Mhm.
okay if we put two independent variables which are have a causation relation into the same model?
Causation relation.
Yeah.
What are they? And what is your dependent variable, and what are the independent variables you are talking about?
So, for example, I'm doing a consumption function with consumption being the dependent variables.
Mm-hmm.
So, is it okay if I put saving and interest rate into the same function as dependent variables, knowing that in practice the interest rate has a causation relation with the saving?
Mm-hmm. So actually here, uh, you can see that there is an obvious, actually a quite obvious relation between consumption and saving. So consumption and saving are part of the are part of the income. If you have a high consumption, then you will have less saving. And if you have less consumption, and then you will have a high saving. So usually you can, the better independent variable here will be the interest rate. Okay.
Yes.
Do not use saving. You should not use saving to explain for consumption.
Okay.
Okay, and usually because there is a causation relation between consumption and saving, okay, which means there will be a correlation between them. Is it? A
Yeah.
correlation between saving and the interest rate, right?
Yeah.
And because of that, the correlation will call your estimate less precise, less reliable. Okay, as you see in the chapter 3 about multiple regression model, high correlation among the regressors or among the independent variables will cause the OLS estimate to be less precise, to be less reliable. So you should not put two independent variables that has high correlation into the model. Just pick one.
Okay.
Yeah,
Understand.
yeah.
Thank you. Uh,
Okay.
and can you show me the result of the previous exercise? I need to check it, but
Which one?
yeah, the exercise that you've just given
Oh,
us.
okay, okay. Yeah.
I didn't check it in time.
All right. Okay. So this is, yeah, this is the exercise that we have just talked about. Wait a minute. Have you come back yet? Hello there. Anyone there?
Yes.
Yes.
Okay, good.
We're
Now,
back.
yeah, okay. So let's continue our lecture. We have just done with the test of significant approach. We still have one more approach to test for regression coefficient. Okay, an individual regression coefficient, that is the p-value approach. So p-value approach. What is p-value? So um, if alpha is the level of significance, so p-value is the practical level of significance. Okay, so p-value is something close to alpha, something like if we have t, observed value of t and critical value of t to compare with each other, then we would have p-value and alpha, the level of significance, and the practical level of significance to compare with each other. So p-value is the minimum. Okay, p-value is the minimum level of significance that the null hypothesis can be rejected. Okay, so p-value here. So in order to do the all right, so we will talk about the steps to use p-value approach to test for an individual regression coefficient first. Then we will define the meaning of p-value in our step here. Okay, so these are the steps that you need to take in order to use p-value approach to test for an individual regression coefficient. The first one, step one, is just state the hypothesis. Okay, like every other test. The first step is to state the hypothesis, HO and H1. Okay, the second step is to find the test statistic. For the p-value approach, you also have to find the test statistic. All right. But step 3, instead of finding the critical value of t, you will find the p-value associated with the observed value of t. Okay, so now let's see how we can find the p-value associated with the observed value of t that we calculated we calculate in step 2. Okay, now let's talk about p-value. Okay, so for example, the p-value, the value of p, okay, will be determined based on the test you are using. Okay, so in order to determine the value of p-value, you have to know what test you are using. For example, you may want to use a two-sided test with HO. Is that beta z is equal beta z star, and H1 is that beta z is different from beta z star, a two-sided test like this. So the alpha, the level of significance here, is determined. Okay, so let's talk about alpha first, the level of significance. Level of significant alpha. Okay, so this t, and this the expected value of t, and this a t distribution. Okay, we have minus t alpha divided by 2 and t alpha divided by 2. Okay, then alpha is the area outside the critical value. Okay, so we have here the sum of these two areas is alpha. The area outside, okay, to the left of minus t alpha divided by 2, and to the right of t alpha divided by 2. This one is the level of significance. Now let's find the p-value associated with this test. So in order to find the p-value, you have to calculate the observed value of t first. Okay, you calculate the observed value of t, and p-value here will be the practical. Okay, we have practical level of significance. Okay, which is p-value. Okay, it will be the level of significance associated with your TS, with your observed value of T. Okay, this one is alpha is the level of significance associated with the critical value of T. Then p-value will be the practical level of significance associated with the observed value of t. All right, so here this is how we determine p-value for a two-sided test. Okay, now here is the all the observed value of t, and if the expected value is 0. For example, this one is our TS. Okay, this one is our TS, and okay, opposite. Okay, from 0 we have here is minus TS. All right, so this is the distribution of T like this. We will have p-value in this case is the value, is the area. Okay, is the area to the right of the positive TS and to the left of the negative TS. Okay, and this one, the sum of these two areas will be the p-value for a two-sided test. Okay, this one, the sum of these two areas will be the p-value for a two-sided test. All right, so now for the case of a two-sided test, what is the this one is the reason of rejection. Okay, the dark one here are the reason of rejections for a two-sided test. All right, we reject HO when we have the absolute value of the observed value of T is greater than the critical value of T, right? Okay, so here, suppose that our observed value of T is here. Now, suppose that our observed value of T is here. In this case, do we reject the null hypothesis? In this case, do we reject the null hypothesis?
No.
No, yeah, because the absolute value of T, of the observed value of T here is less than the critical value. Okay, so in this case, we do not reject the null hypothesis. So what is the value of p-value here? Yeah, we have minus TS. Okay, so p-value will be the pink area. What is the value of what is p-value compared to alpha in this case? How is p-value associated with TS compared to alpha in this case?
It is greater than alpha.
Yeah, p-value here is greater than alpha. Okay, and in this case, if p-value is greater than alpha, then we do not reject HO. Do not reject HO. Okay, but for the case, if we have TS here, and we have minus TS here, okay, what is p-value compared to alpha?
P-value is smaller than alpha.
Yeah, p-value is smaller than alpha. Okay, then we will reject HO. Okay, so here if we have p-value is smaller than alpha, then we will reject HO. Okay, the same happen for one-sided test. Okay, all right, now for one-sided test, for example, we have HO is beta Z is less or equal than beta Z star, and H1 is that beta Z is greater than beta Z star, for example. Okay, so for this one, the alpha, okay, alpha of this one, we have here is T, all right, and the rejection zone for this one is when T, the observed value of T greater than T alpha. So here we have, here's T alpha, and the reason of rejection is the area to the right of T alpha. This one is alpha. Okay, now let's determine the p-value for this test. We will have to calculate the test statistic first. Okay, test statistic here will still be beta z hat minus beta star divided, okay, beta z hat minus beta z star divided by the standard error of beta z hat. Okay, and all right, okay, so here's the distribution of t. And for example, this one is our TS. Okay, for example, this one is our TS. Okay, so p-value here will also be the area to the right of TS. Okay, if for this test, alpha is the area to the left of critical value of T, then p-value will also be the area to the right of the observed value of T. Okay, this one is p-value. Okay, p-value here. So for this test, we reject HO if the observed value of T is greater than T alpha. Okay, now for this case, suppose that our TS is here. Okay, suppose that this is our TS, and this one will be our p-value. Okay, p-value here. Okay, what is p-value compared to alpha?
P-value is greater than alpha.
Yeah, it's greater than alpha. And in this case, do we reject HO?
No.
No. Yeah, we do not reject HO. Okay, but for example, if our TS is here, then p-value will move to the black area. Okay, so in this case, how is p-value compared to alpha?
P-value is smaller than
Yeah,
alpha.
p-value is smaller than alpha, and in this case, we
reject HO.
Yeah, reject HO. Okay, you see the same decision rule as in the two-sided test. Okay, as long as p-value is smaller than the level of significant alpha, then we can reject the null hypothesis. Okay, and you can see the same for this one-sided test. The last case where we have, okay, when we have HO is that beta Z greater or equal to beta Z hat, and H1 is that beta Z is less than beta Z hat. Okay, and we have the rejection zone for this one is when T observed value of T is less than the minus alpha. Okay, so here is our T. All right, the expected value of 0, and this is our minus T alpha. Okay, and the area to the left of minus T alpha is our level of significant alpha here. Okay, and then we have to calculate the observed value of T, which is beta z hat minus beta z star divided by the standard error of beta z hat. Okay, and the way we determine the p-value associated with this TS is the same as the way you determine alpha. Okay, so here's the T distribution. Suppose that our T minus our TS is here, for example, then p-value will be the area to the left of TS for this test. Okay, this one is the p-value, the area to the left of TS. Okay, so in this case, if our TS is here, all right, then our p-value will be the pink, will be this pink area. And in this case, you can see that p-value is greater than alpha, and we do not reject HO because T alpha is not less than the minus T alpha, TS is not less than the minus T alpha, then we do not reject HO. And when we have TS here, which is smaller than the minus T alpha, and then we will have here the black area. This one is p-value. Okay, then in this case we have p-value. It is obviously less than alpha, and in that case we will reject HO. So there's only one rule for using the p-value approach. As long as p-value is less than alpha, then we will reject the null hypothesis. Okay, only one rule for p-value approach. As long as p-value is less than alpha, then we will reject HO. The difference here is that the way we define p-value for each test. Okay, each test has its own way to determine, to define the p-value. You have to find the p-value associated with the observed value of T for each test. Okay, but the rule, there's only one rule. P-value is less than alpha, then we reject HO. Okay, you will apply the same rule for many other tests that can use the p-value approach. Okay, as long as we have p-value less than alpha, then we can reject the null hypothesis. Okay, so how can we find the p-value associated with the observed value of T? Okay, so you can use the Excel functions. Okay, so last time when we find the critical value of T, you use the function T dot INV dot 2T or something like this. Okay, but for the p-value associated with the observed value of T, you will use the function T dot dist. Okay, now for two-tail, please use the function T dot dist dot 2T. For right tail, you use the function T dot dist dot RT, and left tail we will use the function T dot dist. Okay, and in the parentheses you have to provide information about the TS, the observed value of T, and the degree of freedoms of the distribution. Now, for example, okay, so Excel. All right. In the previous exercise, we have the observed value of T is 3.75. Is it? in the previous practice exercise?
Yes.
Yeah, okay. Now we can use the p-value approach to test for the hypothesis. So our hypothesis here is that HO is beta 2 or beta TS less or equal than 0, and H1 is that beta TS is greater than 0. Okay, we have the observed value of T here. This one is a one-sided test. Okay, one-sided test, and which is a right-sided test. Right-sided test where we have the larger side in the alternative hypothesis. All right. Now, the observed value of T here is 3.75. Okay. Now we have to find the p-value associated with that with that observed value of T. All right. Because this one is a right-sided test. This one is a right-sided test. Then we will use the area to the right of the observed value of T. Okay, p-value will be the area to the right of the observed value of T. Okay, so to find the p-value in this case, we will use the function T dot dist dot right tail RT. Return the right-tailed student T distribution. Then you click here. You will provide the information of the observed value of T, which is 3.75, and the degree of freedom, which is 27. Okay, and then enter. Okay, this one is the p-value associated with our observed value of T for a right-sided test. Okay, so what is the level of significance for that test? What is the level of significance for that test?
0.01.
Okay, 0.01. Okay, then this p-value is less than the level of significance, right? Then we can reject the non-hypothesis. All right. Okay, we can reject the non-hypothesis because the p-value here is less than the level of significance. Okay, so you have to determine whether the test you are using is a two-sided test or a right-sided test or a left-sided test. If it is a two-sided test, then you will take the area p-value as the area to the left of minus of the negative number and to the right of the positive number. Okay, and if it is a two-sided test, it is a right-sided test, then p-value will be the area to the right of the observed value of T. If it is a left-sided test, then p-value will be the area to the left of the observed value of T. Okay, now that is how we can determine the p-value associated with an observed value of T for each type of test. Okay, actually in in practice in research, researchers usually use p-value approach because the information of p-value is usually provided in the regression output generated by econometric software. Okay, for example, like in Starter. Now, let's open Starter to see where is our p-value here. Okay, I will use, for example, I may use the file that we have last time. When input the data here first, for example, weight 2, the file that we use for the practice exercise for chapter 1 and 3, so 1 and 2, sorry. Then we have, okay, we have our variables here. For example, I want to regress wage on edu, expert, IQ, for example. Then enter. All right, now we have the estimation output generated by Starter here. I will open it in a Word file so that you can see it more clearly. All right, so this is our estimated model. Okay, the estimation output generated by Starter. Okay, so last time we have been talking about this column, the estimated coefficient and the standard error of the estimated coefficient. We haven't talked about T and P, this one yet, because we say that we haven't studied, but now we have already studied it. Okay, look at this. T here is the observed value of T calculated in step 2. Observed value of T calculated in step 2 for the test with the suspect value of 0. Okay, so for example, you might want to test whether our regression coefficient on edu is statistically different from 0, or you want to test whether it is statistically greater than 0 or not. Okay, then the test statistic that you calculate in step 2 will be this one. Okay, of another example, for example, the regression coefficient on IQ. Okay, you want to know whether the regression coefficient, the actual regression coefficient, the unknown parameters, the actual regression coefficient on IQ is statistically different from 0, or whether it is statistically greater than 0 or not. Okay, then the observed value of T that you calculate in step 2 will be this one. Okay, or whether you want to know whether the intercept is statistically different from 0, then the observed value of T will be this one. So the column T here represent the observed value of T for the test, where we have the null hypothesis is that the beta z is equal to 0. All right, so we have the suspect value here is 0, and that is usually what researchers want to find in their research. Okay, that is what researchers usually want to prove, want to find out in their researches. Usually we want to see whether this independent variable actually has an effect on the dependent variables, or we want to know whether this independent variable has a positive or negative impact on the dependent variable. Not. Okay, those are what researchers usually want to find in their researches. So those answers can be those questions can be answered using the observed value of T in this regression output. Okay, let's try it. Okay, so here this one is the observed value of beta 1. Okay, we have beta 1 hat here, and the suspect value of is 0, and we also have the standard error here. So just take this one divided by this one, you will get the value of 8.23. Okay, all right, this one is the observed value of T for the suspect value of 0. Okay, now what about this one, this column? This column is the probability, okay, the probability P, probability that we can observe a T, that we can observe a T with the absolute value is greater than the absolute value of this observed T. Okay, P value here, this column is the probability that we can observe a T with an absolute value greater than the absolute value of the observed T. Okay, so what is it? This P column, what is it? It is the p-value of a two-sided test, right? It is the p-value of a two-sided test, the probability that we can see a t-value with the absolute value greater than the absolute value of this observed t. Okay, so this one is the p-value of a two-sided test. Okay, so if we want to know whether education has an individual effect on wage or not, you just have to look at the p-value here. So the p-value here is very, very, very small, okay, which is less than 0.01. Okay, so obviously at 1% level of significance, you will have the independent variables education actually have an impact on the dependent variable wage. Okay, and the same happen for other regression coefficients. Okay, they are all statistically significant because p-value here is too small. Okay, for using p-value approach, if you are using a p-value approach, you just have to take the p-value generated by the regression output and compare it with the level of significance. You don't have to look up for any critical value. Okay, you don't have to look up for critical value of t or something like that. Okay, you just have to compare the p-value here with the level of significance, and then you will get the answers. Okay, that's why in practice, in researchers usually use p-value approach to draw a conclusion about our regression coefficient. Okay, now this column is the p-value for a two-sided test. Now, for example, I want to conduct one-sided test for our regression coefficient. For example, here, education. I see that in this sample, okay, our estimated regression coefficient, which is beta 1 hat, is greater than 0. So I believe that, okay, the actual value of the parameters, the actual value of the regression coefficient on SU, okay, is also greater than 0. So it will be a right-sided test. Okay, it will be a right-sided test. How can I calculate the p-value of that right-sided test based on the p-value of a two-sided test? How can I do that? How can I calculate the p-value for a one-sided test based on the p-value of a two-sided test like this? Hmm?
I think divided by 2.
Yeah, right. Yeah, exactly. So remember that for one-sided test and two-sided test, the observed value of t is not changing. Okay, the observed value of t is not changing. That's why for one-sided test, you can determine the p-value of a one-sided test by taking the p-value of a two-sided test and divide it by 2. All right. So for example here, this is okay, this is t0, and for example, this is our ts. All right, our ts is here. Okay, so for two-sided test, we want the area to the left of minus ts and the area to the right of ts. Okay, this one is the p-value of a two-sided test. Okay, for two-sided test. Now, for one-sided test, we just need the area to the left or to the right of the observed value of t, which is not changing here because our suspect value here is not changed. Okay, we have the same suspect value, so the observed value of t is not changing. So for right-sided test, we will need the area to the left of t observed value of, to the right of the observed value of t, which is this one, Okay, so p-value for a one-sided test here, will be the p-value of two-sided test. Okay, and divided by 2. Okay, that will be the p-value for one-sided test. Okay, but now if I want to conduct a left-sided test, which means that I need the area to the left of the observed value of t. Okay, in that case, I want to know whether the actual value of the regression coefficient on education is less than 0. What will be my p-value in this situation, in this test? What will be my p-value here? For the left-sided test,
Divide by -2.
we will need the area to the left of our observed value of t. In this case, our observed value of t is a positive number. Okay, so if our t value is a positive number and we want to test the opposite of what we are seeing here, we are seeing that the sample statistic beta 1 hat is greater than 0. Okay, but we want to test the positive, okay, the opposite of that, which means that we want to test whether the actual value of the regression coefficient on SU is less than 0 or not. Okay, then you have to take the area to the left of the test statistic, which is a very large p-value here. You just have to take 1 minus p-value of two-sided test. Okay, and divided by 2 like this. Okay, and divided by 2. This one would be the area to the left of our observed value of t. In this case, t is a positive number. Okay, so remember that whether you are testing what you see in the sample or the opposite with what you are seeing in the sample, okay, it will determine the p-value, the corresponding p-value. Đợi cô một chút nha. Alo. Ok, đợi tí nha. Okay. Any other questions? This is how you can determine the p-value associated with the observed value of t. Any other question? Okay. Cứ nói đi ạ.
Cái standard error đấy có cho sẵn không cô trong đề thi?
Standard error. Đây ạ, standard error thì nó có ở trong cái estimation output đây rồi.
Ví dụ như thi thì nó sẽ cho sẵn đúng không?
Yeah. Các bạn cứ yên tâm là khi làm một cái bài tập nào đó thì cô đều phải cho sẵn các cái dữ liệu để các bạn có thể làm được ở ngay trên cái bài thi đó, chứ các bạn sẽ không phải sử dụng bất kỳ một cái thiết bị nào khác ạ.
Ví dụ như cái nãy Excel thì cũng thế đúng không? Không cần.
Yes. Đây là cô hướng dẫn các bạn cái cách để chúng ta thực hiện, các bạn có thể thực hiện tự mình thực hiện ở trên máy. Còn về bài tập ấy thì các bạn cứ yên tâm là khi mà cô đã yêu cầu các bạn làm một cái bài tập nào đó thì cô sẽ phải cung cấp đầy đủ các cái thông tin để các bạn có thể làm được ạ.
Cảm
Okay. Any other questions? Okay, no? All right. So I have an exercise here in the next slide. So at home, please do it. Okay, do it at home and answer the questions here. Okay, okay, using the approach. Okay, maybe you can use confident interval approach. You can use have a significant approach. You can also use p-value approach to test the hypothesis in these questions. Okay, and then all right. Answer. Okay. So if you have any questions, if you cannot do anything, you can send me a message or write me an email to ask, and I will answer you. All right. Okay. If you don't have any other questions, so our lecture will end here. You can find more exercise in the book. Okay. Look at the book at the end of each chapter, chapter 5 and chapter 8. You can find more exercise on these problems. Okay. All right. So goodbye and see you on Friday. We will continue with the multiple restriction test. Okay. Multiple linear restriction test. All right. Bye.
Goodbye.
Can I ask you a question
Goodbye,
about
teacher.
group
Yeah.
work?
Tobias, do you have any questions?
Yes, about the group work. How many independent variables are we supposed to add at least to our model?
There's no questions to that, no answer to that questions. You have to base on previous researches and economic theories to determine the important variables, okay, the important independent variable that you need to include in your specification. All right, there's no enough answers for the no answer for the questions of enough. Okay, uh, you have to find the economic theories relating to your topic. You have to find previous researches relating to your topic to see what are the independent variables that they use in previous research or suggested by economic theories to explain for the dependent variables. Okay.
Okay.
Yeah, for some cases, there's maybe only 3 or 4 independent variables in the model. But for some cases, you can see that there may be more than that. Maybe there's 6 or 7 or 8 important independent variables that explain for the value of the dependent variables. Okay. All right. Any other questions? Okay, no. So see you on Friday. Bye-bye.
Bye.
Bye.
Goodbye.
Goodbye, class.